Now, let us go ahead and look at the same cross section that we have been using it for the previous modules as well. It is a 1 meter deep beam, it is an I section with 500 by 200, and then you have some area of pre-stressing steel that is given here, and it is initially stretched to 0.0065 strain, and I have a constant eccentricity of 100 millimeter, that means from the bottom face. So, basically what we are saying is the eccentricity is, this is the eccentricity, right. So, from here to here is the eccentricity we have calculated in the previous class. Okay. So, this also you can say this is 500, right. So, this is 500 and then this is 100. So, the eccentricity is going to be 500 minus 100, which is going to be 400 millimeter, right. And we are going to use M30 and M60 and for two values that we are going to do the calculations, right. And we are going to use also try approximate method, and you know we are going to use idealized design bilinear curve for pre-stressing steel from IRC 112. Okay, now let us see how do we do that. The effective depth now becomes 1000 minus 100, which is 900 millimeter. As we have seen first case, step is to assume XU equal to DF, treat this as a rectangular section. So, this helps me to treat this as rectangular section, okay, with B is equal to BF equal to 500 millimeter. Now, delta epsilon P we know, which is from strain compatibility, which is 0.0035 minus D minus XU by XU, which is 0.01225, and the total strain will be again delta epsilon P plus epsilon Pi, which is 0.01875. Stress is going to be, now we are using bilinear curve again, right. So, we take this curve, right. So, Fp epsilon P, right. So, this is about 1400 something that we take, right. So, using this I get this strain is 0.0072 and this is 1407.8. So, we are somewhere here. So, you do the interpolation and you get your stresses 1571 megapascal. Now, the tension force is stress multiplied by the area of pre-stressing steel, this is your AP, and you get your force as 1879. Now, Cu, if you look at it, it is 0.36 FCK instead of BW. Now that the neutral axis is within the flange, I put BF. So, you get these values 2160 kilonewton. Now, you see that compression force is working out to be higher, then I have to decrease the XU. So, the neutral axis decrease the XU. That means the neutral axis is still going to be within the flange, right. So, for 200 if it is going to be within the flange, I mean when you reduce it, obviously it is going to be well within the flange, and that is a typical thing that will happen when you have a low reinforcement ratio, and you do not need large compression area to satisfy the equilibrium, right. So, let us assume. So, now we are going to further reduce to 176 millimeter and repeat the process with delta epsilon P, I work it to be 0.0143 and epsilon P working out to be 0.020 and FPU you see 1588 and TU is 1899 and you get close to 1900 kilonewton. So, you can say that nearly they are same. So, this XU will satisfy the equilibrium condition. Now, my moment resistance is compression force times the lever arm. So, this is your lever arm Z, which is D minus 0.42 XU, and I get moment resistance of 1569 kilonewton meter, right. And epsilon C curvature now 0.0035 by 176, I get a curvature of this, right. So, you see here this is the strain. So, it is really stretched, okay. It has gone beyond its yield, right. So, the yielding strength as per this was only this, right. So, this is an under reinforced section, right. So, this was your FPY, right, and so we have gone much behind that. So, that means the steel has actually yielded as per the curve, right. Okay. Okay, so right, so we are doing this for 600 now. Okay, hold on. Right. Okay, now we are going to repeat the same exercise for M30 grade. Okay, we initially took M60 grade. Now, if I change the concrete grade, let us see now what is. So we repeat the same exercise. Effective depth is again 900 millimeter. I am assuming XU equal to 200 millimeter, and so once I assume XU equal to 200, then till I'll be treating this as a rectangular section with B is equal to BF, and strain gradient using delta epsilon P. I can get from your similar triangle, and that value is 0.01225. Now, epsilon P is 0.01875. The stress is 1570 again. Now, tension force you see here TU is 1879. Now, the only thing that it is going to change is 0.36 FCK. Now, FCK has become half instead of 60. So, you see here now the compression force is 1080 kilonewton only. Cu is actually now has become lesser for a lower grade, right. So, you see here now we have to increase XU because the tension force is higher than the compression force. So, I have to increase the compression force. The compression force, the only way I can increase is by increasing your XU, right. So, the moment you increase your XU, now the neutral axis will be lying within the flange. So, now how do we do that? Okay. So, now let us assume XU to be greater than the 7/3 of DF, okay, right. So, if so basically what we are saying is DF is going to be lesser than 3/7 of your XU. So, that means you will have constant block of 0.447 in the flange region, right. So, we are taking XU equal to 470 millimeter for this, then as again using strain gradient we get a value of 0.0032 and your strain as 0.0097 and stress again using bilinear curve you get your 43.1 megapascal. Your tension force again is stress FPU multiplied by AP will give me this, right. Now, in compression force that we are trying to do is we are decoupling them into two things. One is from the treating that section, the entire section as one web and the outstanding flanges as a separate thing. Now, compression force for satisfying the web only is 0.36 FCK BW into XU, that is 761.4, and for flange because we have assumed XU is greater than 3/7 of DF, everything will have 0.447 because your depth of the flange is less than the constant region where the stress block which is equal to 3/7 of XU. So, your entire stress is 0.447 FCK. So, if you substitute that you get 938.7 kilonewton. So, when you add both of them 938.7 plus 761 it is working out to be 1700 kilonewton. So, compression force is less than TU. So, you increase your XU, right. And so, we see here still we have not achieved the equilibrium, right. So, compression force is still less than TU, but we have increased by increasing the neutral axis. Cu has increased from the previous trial, but still it is less than 1700. So, you see here compression is 1700, this is 1726. They are getting closer, but it is not still equilibrium is satisfied. So, we can do one more trial. So, I have to now what I have to do is again further increase XU, maybe instead of 470 slightly I have to increase it. So, let us see now if a 470 from 484 if I make it and I redo the same process, delta epsilon P now is 0.003 and epsilon P is this, right, and FPUs from constant equation is this, and TU now is 1723.2 kilonewton. Now, CUW is 0.36 FCK BW into XU, so that is 784.71 kilonewton. Again compression force if you see here, now what is the depth of the flange that we have had. So, depth of the flange is 200 millimeter. Now, what is 3/7 of your XU, which is 3/7 of your 484. So, you can see that. So, you will find that DF is less than 3/7 of your XU. That means the entire flange will be in this 0.447 FCK stress. So, if you substitute that, you get 938.7 kilonewton, and you find that now close, the equilibrium condition is satisfied. So, you can now calculate. Now, you see here C is approximately equal to Cu, then you can get your APF and so on, right. So, you get nearly the equilibrium condition is satisfied. Now that we have done the satisfied, so now I am going to calculate now the each individual area of pre-stressing steel, and you can see 651.7 millimeter square. The area of web is 544.4 millimeter square, and moment resistance, now I can take all the forces as this web contribution and flange contribution. Now we have already done how to do the moment resistance calculation. So, you see here this is APW times your FPU times your lever arm, this is your APF times your FPU times your lever arm. Okay, so you get your total force as moment resistance as 1300 kilonewton meter, right. So, we have seen, so for the web contribution, this is your lever arm. So, we have seen that, right. So, that is nothing but your D minus 0.42 XU, and this lever arm is nothing but D minus 0.5 DF, right. So, you take moment from each section about the tension force. Tension force location is fixed because the area of steel is fixed. So, you take the moment only about the compression force at the location of steel. So, see, that is the reason we get this, right. So, we get the force times your lever arm will give you the moment resistance. Now, my curvature at failure for this flange section is 0.0035 divided by, actually this is, we have actually satisfied the equilibrium condition, right. So, 484 is what we had. Okay. So, we get 7.23 into 10 to the power minus 6. Okay. So, now for this is again for approximate method. Now, we are going to look at how to get using approximate method. So, now you see effective depth is again 900 millimeter, XU is equal to DF 200. So, again this is for approximate, right. So, treat this as a rectangular section, again AP is this, reinforcing index is this, then you go back to the table 11 and you get your stress, which is 1618, and you get your tension force, compression force is this. Again you see here, XU is less than DF, so treat the section as a rectangular section, right. And because XU will be less than DF, so that means this flange section is actually going to act like a rectangular section. Now, for post tension system, from the table again XU by D, once you calculate your WP, you can go directly to the table and get your neutral axis depth parameter, which is 0.178, and multiply, you get your neutral axis depth as 160 millimeter. Tension force is this, that is 1936 kilonewton. Compression force is this. You see here again the issue here is moment resistance, if I take the tension force, it works out to be 1612 kilonewton meter, and curvature is 21.8 to 10 to the power minus 6. So, this simplified method, you can see that it cannot be used for M30 grade, as the neutral axis is actually lying in the web. Okay. So, we can actually cannot be used. It is better to go for strain compatibility method, that what we have talked about in the previous slides. So, let us quick comparison of both the methods. Again you can see here, if I use strain compatibility approach, again equilibrium is satisfied, here equilibrium is not satisfied, but and but somehow I am able to get the moment resistance as a coincidence. They are getting very close, both of them, they are not very far off, but however is not exact, right. So again this moment 1612 kilonewton is based on the tension force. If I calculate using 1730 compressive force, I get a conservative estimation of 1441 kilonewton meter. So in a way, what we can say is, if at all you want quick calculations using an approximate method, always you take the least force. That means here in this case it should be 1730, not 1936. Then your estimate of moment resistance will be done in a conservative way, right. But I think the moral of the story here is, I would not recommend using approximate method, because as the name suggests, it is approximate for quick calculations. Strain compatibility will give you the correct rational estimate of your moment capacity. Okay, again summary, and you can see here that for M30 grade with same amount of steel, I get moment resistance of 1300 and curvature of 7.23. By pushing it to M60 with the same amount of steel, you see here, you are not increasing significantly the moment capacity. The reason is, both of them are under reinforced section. When the concrete section is failing by steel yielding, by changing the compressive strength, you will not get much benefit. Okay, that is the reason. So in flexural demand, you have to play with the steel. Either you have to increase the steel, or you have to use high grade steel to get higher capacities. But changing the concrete strength will not give. So you see 1300 to 1500. So you see it is not even about 15% or so that I am getting, probably, right, in increase in your moment capacity. So increase of but what it helps is, your curvature increases. Okay, that's what I say. Increasing the grade of concrete makes the section more ductile, along with some marginal increase, but not much. Okay, only marginal increase. So, but if you want more ductility, then you can go for slightly higher grade of concrete with this kind of tension control failure. So that will, again, the neutral axis will become less, your curvature will become more, right. So, but if you want capacity, then the best way to put more steel, not really in terms of increasing capacity, increasing grade of concrete. Okay, so let's summarize what we have discussed in this session today. We have explained the stress strain distribution at ultimate state. We have calculated the ultimate strength for a rectangular section and a flange section using strain compatibility method. We also discussed the limitations of approximate code provisions. We solved examples. Again, we discussed the methods for calculating for the flange sections as well, right. So with that, we will complete this part of the module. We will continue the discussions in the next week.